Hello, fellow problem solvers. So today we're going to be doing a problem from the 2021 European Girls Math Olympiad, problem number 3. I suggest you try this problem out for a minimum of an hour and a half, ideally 3 hours, but not more than 4.5 hours. If, on the other hand, you would like to go along with us, I suggest you draw the picture and try to solve the problem for half an hour. So now, let's begin. So, the first thing you notice in this problem is, as you're drawing it, as you draw E and F, BAC is obtuse, a weird condition, and then you draw E and F, and you see, it's this external bisector of BAC with these altitudes from B and C, very interesting. And then M and N are parts of this thing, such that this angle equality holds. It's a very weird sort of picture. And for me, the immediate thing I see that it's missing is the orthocenter, is this point up here. And the reason I say it's missing, it's almost as if this type of configuration is meant to be obscure. It's meant to get you to look at something that you shouldn't look at. And to me, the first thing was, let's just rename these points. Let's call this a triangle ABC with a regular one, not a obtuse one, with the orthocenter H, and let's define E and F here. Let's call this B1, C1. And now let's work with this sort of picture in mind, because it's a much nicer view, to me at least personally, because I know a lot about the triangle ABC and when all the altitudes are put down. Now from here, there are really two ways that you can go about this problem. One thing you can do is you can just add points one at a time. I mean, the points M and N are going to come in pretty soon, but you can look at what do we have from these E and F. And what you figure out also depends on the extent of your background knowledge in geometry. And I say this because geometry is really the one discipline where you can really build up a lot based on previous problems that you solved. So, okay, we're going to have CE. So let's maybe look at, okay, this is a bisector right here. These are both alpha half, alpha half, alpha half, alpha half, which means these are both beta half plus gamma half, which gives us AE is equal to EF. We're just exploring what's true about these points. So we have this is true, and then we also have EC1 over EB is equal to C1H over BH, and then this is equal to, because these are concyclic, this is equal to what? C1, I think it's over B1, yes, B1H over CH, and then this is also equal to B1F over CF. And furthermore, we can also get this immediately, because this is 90 minus alpha. We know that, what's this called? This is C1H over BH is really what? The sine of 90 minus alpha, i.e. all of this is equal to the cosine of alpha. So that's not too bad. We can immediately calculate all of these things if we need them in the future. And now here, before I introduce the points M and N, I invite you to take 20 minutes and see what would you do with points M and N. What are the things that you would do to connect them to all the other points in the triangle? And the reason I would invite you to take at least 20, ideally 40 minutes even, to work on this is because depending on your ideas, there's going to be a different solution. And this problem has many solutions. It's a beautiful, nice geometry problem. It is not trivial by any means of the imagination, but it's also not incredibly, impossibly difficult. Like, for example, it's not like IMO 2011 problem number 6, where you just have to be really good. This is a couple of steps below that. So now that you've hopefully paused, what I would do is draw a better diagram, namely something like this, where I have now A, I have E, F, H, and I added a point M as well. And an important note about construction. So the condition is that HME is HCB, like when I reintroduce A, and H, I just switched their letters. And what I have here is, this is 90 minus beta, because this is equal to this. But that implies, because this plus this is equal to this, that means that this plus this is equal to this. So this must be equal to this. And this is another way to look at the same condition. Namely, we have point M is on the line CE such that HMC, the circle around that, is tangent to BC. And this is also just a thing that we should notice, that BC is tangent to the circumcircle of HMC. Now the question for you is, how would you connect this point M? So this is 90 minus beta. What's true about it? And I will allow this to also be an instructive moment to why good pictures matter. Namely, after drawing A1, I immediately thought for my first picture that A1, M, and B1 were collinear. I thought that was the thing about M that's unique, that's interesting about it. And I would have symmetry on the other side. I would have A1, C1, and N also be collinear. And then I might have some angles that are interesting. So I thought that's what I needed to prove potentially. And this is why it's important to draw not only good diagrams, but it's important to draw different types of diagrams. Like I have A that's pretty long. Like A, B, and AC are not that different. The triangle is almost acute-ish. Maybe we should draw another triangle as well. But the thing is, once you draw another triangle, you see that this just cannot be the case. And this is also why it's important for you to think when you're drawing your diagrams, how am I constructing these points? For example, how do I construct the angle HME is equal to HCB? It's directly not possible. But indirectly, noticing that this angle is equal to this one is a lot more plausible, because it's easier to draw angles like this where you just add a point that makes an angle, as opposed to, like drawing a line at an angle, as opposed to picking a point such that an angle is formed. And now with this, once you calculate all the angles, you see that you don't have anything immediately coming at you directly from all these angles. And also important to note is that you can look at these things differently. You can look at AEF as your main triangle, HA point on the line EF, and then these being perpendicular where they intersect these sides of this isosceles triangle, and then you have a condition that you need to prove. I.e., there are many different ways you can try to think about how you would go about doing this. So now, if you haven't found anything about the angles, that's okay, because there's nothing to be found just with these angles as they are. So it means we'll have to add something to the picture. And now the question is, what would you like to add? Personally, if you have some experience adding points, I would just invite you to pause here and work for 30 minutes on your own without me giving you any sort of hints or pointers. And if you don't, then the idea I would really say is, let's try to draw circles first and intersect different circumcircles of different types of triangles and see if we get any interesting points. Any points that can maybe connect M, E, C together with F, M, and B, F, N, and B. Can we connect F and M somehow? Let's think about interesting points. And if this is your first time really doing this, I would also suggest trying a simpler problem than this one. But if you want to go ahead, I suggest you actually take a little bit extra, take a little bit like 40 minutes and try to add a couple of points, 2 or 3 ideas with circumcircles. If you intersect 2 circumcircles and you find a third one that's also quite interesting, then that's a win for you. That's something you should explore deeply. That is sort of the advice I can give you without giving away what to add. So one of the things I would try out, the first thing I tried out was EHM with something. And I was going to think, okay, what's that something going to be? I said, and I'm using a pencil because I want to be able to clear it out. I'm exploring really. And the other point, I want to have one point of intersection to see if I can connect some angles. And one idea, okay, maybe of A, C1, B1H, maybe this circumcircle. See it intersect again at some point. What angles will that give me? Well, because this is 90 minus beta, this will be 90 plus beta right here. Call this point Q, Q1, like the first intersection that we were trying out. So this would be 90 plus beta. This angle right here would be equal to, this is also 90, this is 90 minus beta as well. So this has some interesting, so this is equals to 90. Wait, so this is 90 plus beta, this is 90 plus beta. Let me write that down. C1 Q1H is equal to the angle EQH is equal to 90 plus beta. Now, is there anything else I can do with this? Maybe take 5-10 minutes and you figure out for yourself if there's anything I can really do with this point Q. And I don't know about you, but I could not find anything useful for this point Q. So Q1 out. Let's try another point. And it's usually just spend 5-10 minutes, see if you find anything interesting. I mean, actually, there's no really universal advice. It's about when you search into depth, when do you explore a point deeply and try to figure something out, and when do you move on to another idea, another point. This is not a thing that has a legitimate answer that's always correct, always universal, but it's an intuition you build up. And for me, I really want to try out a bunch of different things at the beginning, just so I put a lot of ideas on paper before I commit to any single one of the ideas. So now let's try maybe if I intersected EHM with the equivalent. I still like working on EHM. We'll switch it up later if we find anything better. Let's switch it up with this one, this, and we get HFN. If we intersect these two circumcircles, it's a point here, right? And now what do we know about this point? Now this seems a little bit more interesting to me because we have the point E, let's call this point Q2. We have EQ2H is equal to what? It's equal to 90 minus beta. And FQ2H is equal to 90 minus gamma. So together, the point EQ2F is equal to alpha. And we have, it's interesting. It's more interesting than before to me because I have this thing and I have AE is equal to AF. So maybe Q2 has some special properties. And I invite you to pause for another 5 to 10 minutes, even more perhaps if you feel like it, and see if Q2 has any properties that are interesting. I invite you to do that now. So now that you've done this, let's move on to a better picture. Okay, so we have this picture and these conditions. FQ2H is alpha. This is 90 minus beta. This is 90 minus gamma. Now, for me, I actually, once I was doing this, I was like, wait a second. This thing right here is 90 minus beta. And this whole thing is like alpha. So it smells like I should be able to connect it with this. I at least need to try. And once I connected AH, and I realized, wait a second, what is HAE? Wait, that's HAB. Oh, that's 90 minus beta. Like after I saw this, it was immediately clear to me that this thing right here has to be the reflection of A in the line EF. Because the angles, once you reflect a line, then once you reflect a point over a line, then every single, these angles stay the same. And to actually legitimately prove that is I would just write, let A prime be the reflection of A in EF. So A prime E equals A prime F. And you can really just prove this via, and this is equal to AE is equal to AF. And the way you can prove this is via congruency really. Put H, you have EH is equal to EH, HA, EA, these are equal. You have the angles already from the first congruency, AEF, A prime EF, and you can get all these angles. So we know that Q is now interesting. Q is not just any sort of point, it's the reflection of A in the line EF, which makes QA much more peculiar point. It has some other properties. It's not just some any old point. Whereas Q1, when we had Q1, it didn't seem like it had any other special ties to anything. At least not ties that we could find out just from the first couple of minutes of playing around with it. Now, to me, this was a sign to look further. And actually, if you think about it, what you have is you have that the points E, H, M, let's call this A prime now. Q2 is equal to A prime. These lie on a circle. F, H, N, A prime lie on a circle. And what we need is to have E, F, M, N to lie on a circle. So when does this hold if we know these two things are true? What is sort of the equivalent condition? I invite you to take another 10 to 20 minutes and think about this and even try to prove this. And the equivalent condition is, by the inverse of the radical axis theorem, is that a radical axis is just like if you have three circles, then these intersections between them concur at one point. And the converse is true if you have two circles, and if you have two circles and a third cluster of 4 points, you can sort of get a converse to hold. If you have points like this, okay, so if you have these 4 points that concur, then these 4 lie on another circle. But anyway, here we would have that the common thing for this is H A prime. The common thing for these two is E M, and Fn. If these 3 points concur, then we can know that this is in fact concyclic, because we'll have that, mind you, also from the, so if these concur, so what would, okay, so if they concur like here, then we would have at point, say, call this point P, then we would have PH times PQ2 is equal to PM times PC1 from the first thing, but this would also be equal to PN times PF from the second circle. And then we have from the power of point that these 4 points are concyclic. Now, if you didn't have this idea, I invite you to take another 10 to 20 minutes and see how would you prove this. Here's my next idea. So the first thing you can see once you clear the dust is that if HA prime, Fn and EM concur, because Fn is really FB, this is the same as, and similarly EM is EC, this is the same as these 3 lines concurring at the same point. And how do we prove this? Well, there's a tool for this, and it's a trigonometric tool. That's the easiest one to really do here. And it's called the trigonometric triva. Namely, if you have ABC, a triangle, and lines AA1, BB1, and C1, they concur in the same point if and only if the sines of these angles multiply to 1. So if sine of A1 AB over sine of A1 AC times the sine of, we'll have C1 CA over sine of C1 CB times the sine of B1, what do we have? B1B, B1 BC over the sine of B1 BA. If this is equal to 1, then these concur. And the way you prove this is via a lemma that if sine of alpha minus x over sine of x is equal to sine of alpha minus y over sine of y, where x and y are less than alpha and alpha is less than pi, and this is greater than 0, then this implies that x equals y. So this is how you prove this trigonometric triva. And now we can use that here. Like, the thing we need to prove really is that the sine, like we have some of these sines. So we'll have the sine of, what's going to be FBH over the sine of the angle FBC. In fact, I invite you to maybe try to prove this. Take 10 to 20 minutes and try to prove that this trigonometric sine triva is true. It's a very nice proof to like actually finish this. And what is this equal to? So we have FBH. Okay, this is same as FBB1 sine of this angle. This is 90, so this is equal to B1F over BF. Okay, so let's get BF on both sides. Let it cancel out. So FBC, sine of this, is equal to sine of, we'll get the angle gamma, times we have what? FC over BF. And now this whole thing is equal to B1F over CF over sine of gamma. And if you remember from the beginning, B1F over F1C, FC is going to be equal to what? It's going to be equal to H B1 over HC. So all of this over sine of gamma. And what is this equal to? Well, we know this is equal to the cosine of alpha. So what we have is cosine of alpha over sine of gamma. That's this thing. So then we need, so we have FBH over FBC. So then we will have, because FBC was over, we'll have ECB, sine of the angle ECB over sine of the angle ECH. And this will be equal to, similarly to this, sine of beta over cosine of alpha. So what we're left with, the final thing, is A prime. So it's the sine of the angle A prime H. What do we have? So we have this over this, and now we're going to have this over this. So A prime HC over sine of A prime HB. So this needs to be equal for these to cancel out. We need this to be sine of y, sine of gamma, over sine of beta. Now the question is, how do we prove this? Well, also note this thing right here. What is gamma plus beta is equal to what? It's equal to BHC. So we can so just knowing this lemma, and this is why this is such a useful trigonometric lemma. It comes up so often. And I will try to drill this up in you by showing you different kinds of problems where it comes out of nowhere, really. And here, this would mean that because this is this gamma beta, we would have this is sine of really x over sine of beta plus gamma minus x is equal to sine of gamma or sine of beta. We need to find x, and x is obviously gamma, just knowing this trig rule. So what we're left to prove to finish the problem is that the angle A prime HC is equal to gamma, and that the angle A prime HB is equal to beta. And now I invite you to take 5 to 15 minutes and try to prove this. Here's the proof. So this is the picture we have. I'm not drawing a nice picture now because it's not a picture with a lot of stuff on it, so I don't feel the need to draw a very nice picture. So this is what we need to prove, okay? So if this is gamma, what do we have? Well, we know this thing right here, okay? And now, okay, let's do some angles. So this is alpha half, this is 90 minus alpha, beta half plus gamma half. Because this is a reflection, this is alpha half, this is 90, which means this is beta half plus gamma half. Oh, but also this here is alpha half. So we have this is 90. Okay, so we have A prime. Okay. So A prime can really be thought of as perpendiculars from E to BH and F to CH. Yeah, I mean, obviously now when you think about this being a rhombus and this being parallel to this, these things make immediate sense. But nonetheless, let's see. Okay, so we need... This needs to be gamma, which means this angle needs to be 90 minus gamma, if I'm not mistaken. Yeah, so this needs to be 90 minus gamma, which makes this 90 minus gamma. But this angle here is 90 minus gamma because this is 90. So what we need to prove is that when we take these two intersections, that this is parallel to BC. So let's then rewrite the problem in terms of that. Okay, so call these points S and T, and what we need to prove is that ST is parallel to BC. This is true if and only if the angle A prime HC is gamma. So we need to prove this. And this is true if and only if hs over ht is equal to hb over hc. And the reason I'm using line segments as opposed to angles is because I have all of these line segments already. And to be even more truthful, I tried using angles and I didn't get anywhere. So what do we have? hs over ht. Well, both of these are alpha halves, so these are similar triangles. So we have hs over ht is due to the similarity of triangles HES, similar to the triangle HFT. This means that this is equal to HE over HF. And now this thing right here is equal to, because these two triangles are similar, namely the triangles HC1E is similar to the triangle HB1F. So this thing right here is equal to HC1 over HB1, which is equal to, because these two triangles are similar, you can think of it, is equal to HB over HC. So we have this is true, which means this is true, which means this is true, which in turn means that these signs cancel out, and we have that HA prime, BF, and CE concur. Now this solves the problem. And now here I would really invite you to take maybe 10 to 20 minutes and try to write the problem up. And now, instead of presenting you how I would write the solution for this particular type of way of solving the problem, let me present to you a different solution and a different motivation behind the solution. So let's do that now. So the first thing we do is we say rename the point A to H and let A be the orthocenter of the triangle HBC. Now the idea behind this next solution is, instead of intersecting HEM and HFN, those circumcircles, you intersect HMC, because you remember that BC is tangent to both this circumcircle and the other one. So you intersect these two again, and you find them that what you get is that we let Q be the intersection of these two circumcircles. That's different from H. We call these angles what they are. And we have that BQC ends up being equal to alpha, which means that this point Q is actually on the circumcircle of ABC. And this makes Q an interesting point because it has that extra condition that we didn't know to begin with. Now, earlier in the video when I told you to play around with the problem, and if you played around and thought of Q, and you tried something out, I would still invite you to try to take another 10, 15 minutes and work on it a bit more, because I'll try to present the solution, but I'll also give you pauses where you can build up on the solution that you already have. So with that in mind, the next idea with Q is intersect QH with BC. And the reason you're doing this is, remember, BC is tangent to both of these circles. So if I was to draw the other one, draw the point N approximately, and I would have this BC is still tangent to both these circles. So that means if this is point P, what that means is that PB squared is equal to PH times PQ, which is PC squared, which means P is the midpoint of BC. Now I invite you again to take another 5 to 10 minutes and try to push this further. And now the next idea is AQ, C1, H, and B1 are concyclic. And we have this because we know that PB is PC because it's the midpoint. PC, PB squared is PH times PQ. But PB, because this is 90 here, which means this is the center of the circumcircle around BC1, B1C, this means this is equal to PC1 squared, and it's equal to PB1 squared. So these two imply that HQ, C1, and B1 lie on a circle, for which PC1 and PB1 are tangents. And because we know that HC1, B1A lie on a circle, this means that all 5 points lie on the same circle. Actually, my argument is a bit faulty For example, this means that HQC1B, oh, wait a second. The argument actually still can hold, but it needs to be more precise. Because we know these four are concyclic, and we know from this that PC1 and PB1 are tangents to this circle. Now, if we look at the circle around B1HQ, we also have PB1 is a tangent. So what that implies is, actually this just implies because we know, okay, so we know, I see, so we know that these four lie on a circle just because both HC1A and HB1A are 90, so we know these four lie on a circle. And now we use this fact. And the reason we can use this is because this is the power of P with respect to this circle, so we know that Q is also on it. If we did a phantom point, Q prime is equal to PH intersection that circle, we would have PH times PQ prime is equal to PC1, and then we'll get Q prime equals Q. Interesting, but a good learning point here actually, that you need to be careful about concyclic points when you're using just powers of points like this. And now this thing here also implies that the angle AQP is equal to 90 degrees. And now again, I invite you to take another 5 to 15 minutes and try to go take the problem further. Because now I'll go to the next claim, which is that the points A, Q, F, and E are concyclic. And the reason we have this is from the EK being EF being the angle bisector of C1HB and B1HC, we have EC1 over EB is FB1 over FC. And from these angles being the same, from the angles, namely QC1B being the same as QB1C, because these angles are identical, and QBA is QCA, is QBC1 is QCB1. We have these triangles are similar. And now what that does to us is it gives us this relationship. And now we use these two, we combine them, namely we know from the first bit, once we add 1, we'll get C1B over EB is B1C over FC. And now equating the two differently and substituting that for what we had in 2, we get EB over FC is QB over QC. And if you look at the picture, you see EB over FC, that is EB, FC, QB, QC. We have the angle. So we have that this thing, and the fact that the angle QB, QBE is QCF, this implies that the triangles QBE is similar to the triangle QCF. And now this here implies what? Well, it implies that the angle that we need for this equality is that we have the angle QEB is equal to the angle QFC, and this implies that QEFA are concyclic. And now with this, I invite you to take another 20 to 30 minutes and try to figure out the next step. Here's the next step in the solution. The final step being that A, Q, E, and MF are all concyclic, meaning they all lie on the same circle. And the way we prove this is we have Q and F is equal to Q and H plus this is equal to QBA plus ABC, QBA plus ABC, which is equal to the angle QBC, which is equal to the angle 180 minus the angle QAC. But the angle QAC is really QAF. So this is 180 minus the angle QAF. And because QNF plus QAF is equal to 180, this implies that N, A, Q, F lie on the same circle. And because E lies on the circle around A, Q, and F, this implies that N, A, Q, F, and E lie on the same circle. And now with this, we get the similar thing holding for M, purely by analogy. So we have M, N, A, Q, F, E lie on the same circle, which means that E, F, M, and N are concyclic, which proves our problem. And as always, thanks for problem solving.